Good evening, everybody. So this is dynamic programming session number 3, and we are continuing what we have done in the session number 1 and 2. Both the videos are there on YouTube, and if you need any help with the link, you can message me on the Discord. So let's begin this session. All right, we want to carry forward into a different type of problems. First of all, there was an incomplete problem in the previous session. We're going to look into that. And then we are going to continue to a different type of a problem. So without further ado, let's get started. All right, so the problem that we were looking in the previous session was this. Let me just really quickly get a grid. So I am taking intentionally a square grid for now, but it doesn't matter for this problem. It can be any type of grid. All right, so the problem that we are looking at is this, that we have, let's say, some robot, some robot, which is here. All right, now this robot, there's a two-dimensional grid on which it can travel, right? It's a classical DP problem. Let me describe it. It can either go one cell to the right, or it can go one cell down. All right, so those are the two moves that this robot can do. And it needs to reach this target, this destination here. Okay, let's say this is the destination and this is the source. This cell is the source. Then the question is, in how many ways can this robot reach the destination from the source? So one way can be this, for example. Another way can be this. One way can be to go here, then go down, go here, go down like that. And we can come down. Right, so we analyzed this problem in the previous session. So once again, in the last 10-15 minutes, we spent doing this for 2-cell, square, like 4 cells, and like that. So you can visit the video. I'm just going to build on top of it to save some time. So this time, today, I'm not going to show you both the approaches of dynamic programming. I mean, in the sense, I'm not going to do a bottom-up and top-down solution. I'm just going to do one. I'm going to pick bottom-up. And then in the next problems, we'll look at the top-down approach. So the question here is, in how many ways can this person reach the destination? Now, this is a very standard problem. And this type of problem, once again, leads to a whole variety of different problems. So it becomes important in that sense. So let's analyze it. Suppose that we have the template that I'm going to use to code is going to be exactly similar. Once again, to solve this problem, is just this has become a 2-dimensional problem instead of a 1-dimensional problem. Right, so suppose that you had just one cell, all right, and this robot standing here. Then in how many ways can the robot start from here and be here? Like this is the source and this is the destination. Then how many ways can this robot go from source to destination? That's exactly one way, right? There's no other way. Now, if we were to analyze, so how do we build the solution? Let me show you. So if we were to analyze this, let's look at this cell. In how many ways can the robot get to this cell? The robot can either go down or right, cannot come back up. So there is just one way to reach this point. In how many ways can this cell be reached? Once again, just one way, right? All of this row is just one way. There is only one way which is possible, which is really this way. That's it. There's no other way to get here. Similarly, if you look at the column, the first column, okay, so let's say these are the columns, and let's say these are the rows here. Then for the first column, this column 0, in how many ways can the robot go to this place? Once again, the answer is 1. There is no combination here to really judge. But now it becomes tricky here. In how many ways can we get here? So these will constitute our base conditions when we write code. This is going to constitute our base condition. All right, so in how many ways can we reach at this point? Right now, it's humanly possible to compute it. There's one way doing this, and there's one way can be this, and then other way can be this. Right, so those are 2 ways. There's no other way. And as we saw in the previous class, getting to any position, you can either come from top or the left. So for any row comma column, so let's say this is the row comma column, right? For any row comma column, you can either come from either the row -1 comma column, one second, or you can come from row comma column -1, right? So that would be row comma column -1, and this would be row -1 column. So if I want to find the number of ways to get to this, it essentially is basically however many number of ways you can get to this place plus number of ways you can get to this place. So that gives the answer for each row comma column. So this will be 2. Now, how many ways can you come here? 3, 4, 5. 4 and 1, 5. 4 ways you can reach here. 4 plus 1, 5 ways you can reach here. Any question? Okay. Now, just one quick thing. So, yeah, go ahead.
Could you explain once again? Like, still, I was not pretty clear because I just joined a little late. How do you arrive to a formula like a row -1 column? And
let's look at this destination. All right, let's look at this destination. In how many ways you can reach this destination? Like, what would be the previous step to get to this destination? Either you can come from here, or you can come here. Is that correct?
Yep.
So the number of ways to get to destination would be equal to the number of ways you can get to here or here, right?
Mm-hmm.
So that's the formula, essentially.
Okay.
Now, one quick thing, while I'm taking the class, I will not be able to look at the chat. So, I mean, if you guys want to help out each other, you can help out, because I mean, if I look at the chat, then I lose the track of what I'm doing here. So if you have any question, you can ask me directly on unmuting yourself. So I'm going to build the solution from here. All right. And I'm going to go through a top-down approach. That is, I'm going to build from the base condition. I'm going to go fill the array all the way to the destination. Okay. So what my solution is going to look like is something like this. Let me clear this. Right. Let me take another of these five by 5, and let's put it here. So here's what I'm going to do. Right. In order to compute this, at this point of time, I'm just keeping both of them as n. So this is a square, but it doesn't matter. Okay, it's just a square at the moment. So I'm going to construct another cache, right? The usual procedure of how we do things. This cache, and this cache will have n square elements, n columns and n rows. This cache will contain the number of ways to go to these particular rows and columns. So the first element will be 1. Then this will be 1. This will be 1. This I know, right? And I will keep constructing like this. Now, when I come here, all I need to do is compute this and this, add these and this, right? And you can go from there, right? If you were not to do this, right, as I previously explained, if you were not to do this and you were just to call recursion top down, then that would have a different type of complexity, right? Here you will have to do n square computations. So there's total complexity will be n square, right? N square positions you will be doing additions. So for example, at this position, you will be just doing this addition. So there are n square additions, hence n square computations. So this will be very faster compared to the exponential time the normal recursion gives you. All right, so I'm going to come down to writing some code and some pseudocode and code. So if you have any question, you can ask me. Let me just fire up my IDE. Right. I'm going to call this, let's say, grid.py. I'm going to write Python code, but don't worry. I mean, the Python code is pretty simple. It's going to look pretty much like pseudocode, but I will write the algorithm as well first. So suppose that this function, okay, I'm going to define a function. So we call it def. Let's say I'm going to write a function which is called number of ways, and I'm going to pass number of ways n equals to, let's say, 3. So for a grid of 3 by 3, in how many ways you can go from 0 by 0 to 3 by 2, 3 comma 3, not actually 3 comma 3, but 2 comma 2, right? So this essentially means that you're going from 0 comma 0 to 2 comma 2, right? So this should return the answer for my function. So I'm going to define some kind of a function. Let me write the pseudocode first. Okay, so basically what I'm going to do is once again, don't worry about all this. So the first step is to basically create a 2D array. And same size, whatever, create a 2D n by n array. You can write this n cross n array, right? So that's straightforward step. You don't need to worry about it. Then basically initialize all the row 0, and column 0 elements to 1, right? That's this step here. We are this and this. And then basically loop over all the elements, computing the value. And fourth, return the whatever our cache is, let's say whatever the cache is, and then basically n minus 1 and n minus 1 of that element. This last element would be n minus 1, n minus 1. And that will give you the answer. So if you have any question at any point of time, you can ask me, all right? So I'm just going to write a function. In Python, you write function with def now, and this is going to take a number n in it. So the first thing is I'm going to create a 2D array. Whatever language you use, you can create a 2D array in that language. In Python, the way it's done, don't worry if you don't understand the syntax, all right? I'm just going to write a code here. So my array is called memo, and I'm just going to write a syntax which is going to look something like this. And let's just print memo to get the idea of what we are doing here. Right, so we write this code. What did we do? Where is the mistake? Int is not subscriptable. I'm not doing any subscriptable anyway. Oh, my mistake. So sorry. All right. Let's kill this. Let's kill this. And let's run this again. So this is the 2D array, right? This is the 2D array that we have now. So I've just initialized the 2D array. Now I'm going to do the what I was saying. So I'm going to say for row in range of n, that is loop n times, and then for column in range of n. So here row and column are the variable names, and range n is basically numbers from 0 to n minus 1. Right? So I'm going to iterate over each element. First thing is, if it's row 0, if row equals 0, or let's say column equals 0, then essentially make the memo of row and column as 1. Right? So this is the initialization part. Now else, if it is not 0, then basically I need to do this. This equals to something plus something. And what is that something plus something? I'm going to say row minus 1 plus column, and row comma column minus 1. So once again, if it's first row or first column, then the value is supposed to be 1. If that's not the case, then the value would be row minus 1 column plus row and column minus 1 index. And once this whole thing is computed, you come out of the loop, and then you just return memo of once again, Python, people who don't know Python, don't worry about it. I'm just returning the last element, essentially, of this array, of this 2D array, right? And what we can do is you can just print the memo here just to get the idea of what this looks like at the end. So let's run this code, see what happens. And you get the idea as, this is 6. So after the computation, this became the array. And that's the number of ways, 6 ways. You can change it to whatever you want, maybe 10 or something, and then you can compute it. And those are the number of ways in the end you get. So once again, that's the bottom-up approach, that we began from the base condition and then we moved toward the solution, and we found the solution in the end, right? If I was to do this, okay, let's just take it. I'm just going to show you a sneak peek into the top-down approach, and then I would like you to do this by yourself. So if I was to do the top-down approach, okay, let's just define this function again, okay? And this is called, let's say, whatever this, top down, or just call it, let's say, recursion. Let's call this, let's go recursion. Just gonna get rid of this. If I was going to do this, let's say I was going to write recursive solution for the same problem, then what would I do? First, I will have to write a base condition. It's a recursive function, right? So the base condition would be what? In this case, that if n equals 0, then basically return 1. That would be the base condition. Else, I would write, else, let me just make it look more beautiful here. Else, now underscore rec of n equals to something. I will write something there, right? That would be now underscore rec of whatever, n minus 1 plus now underscore rec of n minus 1. Now this is 2D. I'm writing 1D right now, but I want you to try this as well. So that's why I'm not giving you the full solution. But essentially you will write like this. That's the brute force recursion. This will do a lot of computation, but you will have to add some caching so that you can store the results in a 2D cache and then retrieve them, right? And the template is going to be exactly same as all the previous problems that we have done here. So let me, for example, this one, right? This thing, the one that we did in the last class. So you look for a value of cache. If it's not present, then you get the value of that cache by calling the recursive function on the smaller elements. Any question in this problem? Okay, I'll take the silence as no. Now, let's go to the next problem. So these two problems, the stairs and this grid, these problems were based on what the type of problems that I call the number of ways problem. That is, in how many number of ways can you do something? All right. The next series of problems that I'm going to cover are to optimize some value. Okay? So value optimizing problems. So suppose that, let me, just give me a second. Let me write this problem. Suppose that you're here. This is a path in front of you, right? There are that many number of steps. And let's say this is the destination that you want to go to. All right. Now, you can either go to the first or to the second position in one shot, right? So you can either go one step each, or you can just hop 2 steps, or you can do 1 step, then 2 step, then 2 step, 1 step, like that. It's different combinations you have to get there. The only trick is that each step has a cost with it. So if you land on that step, there is a cost that you have to pay. And suppose that the cost here is, let's say 1, 2, 2, 1, 1, 2, 1, 1, 2, something like this. So the question is, in what is the minimum cost in which you can get from source to destination? This problem comes in various flavors. I'm writing a very simplistic version of it, but this comes in a very many flavors, I would say. But essentially it will boil down to this situation that you have to compute the minimum cost of getting to a point from source to the destination, right? So some important things are, these are non-negative, negative numbers. So you always add up cost. Now, how would you solve this problem? How would we go about solving this problem? What would be the brute force approach? The brute force approach can be to compute all possible paths and compute the cost of those paths and then find the minimum cost. Right. Let me go to the DP approach. Let's write this non-negative. When we go to this problem, this type of problem, right, we kind of use recursion. Now, we can build all the paths that are possible using either the backtracking or something, and then we can compute the result of each path. However, when we are going through, when we're going to go through recursion, we can add some kind of a caching and then optimize our results, making the algorithm faster. So let's go through this problem, right? If we are writing recursion, then first of all, the base condition, right? We don't want to solve all the way a hard problem here. We want to reduce the size of this problem to very small cases first. All right, so let's solve for the position number 1. In how many ways? So what is the minimum cost to get to step number 1? Can anybody tell me what would be that cost? What is that?
1.
Yeah, that's right. 1. 1 is the minimum amount of cost you can go to the step number 1. Let's write the cost above with a different pen. So 1 is the minimum cost, right? If that's clear, right? Because there is no option. There is only one step. You have to go to that step, and that's the cost of that step. If there were only 2 steps, right? Only 2 steps, then what would be the minimum cost to get here?
Be 2.
There'll be 2, right? Once again, because they are non-negative numbers. So if you take a previous hop, then essentially you're adding the cost. Now let's go to the third step. Now what is the minimum cost here?
Well, what's the rule? Can we just jump from that to the third?
You can either
spot?
go 1 step at a time or 2 steps at a time.
Okay.
So the minimum cost in this case is going to be 3, exactly, 3,
yeah.
right? Why 3? Because you have 2 choices. You can either go 1 and 3, or you can do 2 and 3, right? There is no other choice. This leads to 3, this leads to 4. But what is the important lesson while we come to this step? What is the important lesson? What is the computation that we are doing at this position? We are saying the minimum cost to reach at the step number 2 is either going to be the minimum cost to reach 1 plus the cost of step 2, right? Plus whatever is the cost of step 2. Or we can, the minimum cost of going to 2 plus whatever is the cost of step 2, right? Those are the only 2 options. So whatever is the minimum of those, we will pick that as an answer. Any question with this? All right. So if for any, we're going to generalize, all right? We generalized for 1, 2, 3, all right. For any n, what can I say? What is the minimum cost of n? It is going to be minimum of, can anybody tell me? That would be minimum cost to get to f of n minus 1, or the minimum cost of getting to f of n minus 2 plus the cost of n, because you're going to come to n position. So n cost has to be incurred. So whatever is the minimum of the 2 is the answer. Any difficulty in this generalization? All right. Similarly, we can say the same thing about the last step, right? The very last step, this. The person can either come from here, or let me use a different pen. The person can either come from here or here. So whatever was the cost to get to this one, or whatever was the cost to get to this 2, minimum of these 2 will lead to this, right? Because if whatever is the minimum, the person can jump just directly to the destination. Right? So let's once again do the same. Let's do this. Let me erase this. And let me show you the structures that I'm going to use to do this. Actually, I'm going to give you guys a minute, all right? Think about this, what I just said. Okay, work it out, the mathematics of this before I move forward. And then I will move forward. I'll just take 30 seconds to do this. All right, I hope you have a clear understanding of this. If you have any question, you can ask me, or you can always ask me later on as well. Now, let's get rid of all this and let's construct the solution for this problem. Oops, sorry. Let's remove this, all of this, and let's begin. Right. So what would I do in this case? Once again, I'm going to use the same approach here with a slight twist. This problem resembles the maximum subarray sum problem that we did. That at each stage, instead of just doing a raw computation, we have to make a decision of choosing the best outcome for that place based on the recent history. All right. So what I'm going to do is I'm going to create an array, which essentially is equals to this same size as original array. Now, this array, which I'm going to call whatever memo or whatever you want to call, what it represents, it's very important. All right. This is the most important thing here, that what it represents is the nth position. That position represents the minimum cost to get to nth position. Right? This is what this array is storing. So when I write first, let's say this is 0. When I write first, the minimum cost to get to 1 is going to be 1. When I write 2, the minimum cost to get to 2, I'm going to write here is 2. So when I look for, let's say 3, then I know already the minimum cost to get to 1 and 2 what is. And then I will add whatever is the cost of this step is, and then the minimum of these two. So that is the decision. At every step I'll keep making, and I will continue building the solution this way till I reach the last element, and then I will get the minimum of this, or this is the answer. Okay, so I'm going to write once again some algorithm and code for this. I'm going to call this, let's say, min cost whatever 1D dot py. So let's call this function minimum cost. All right, let's say minimum cost, and let's say that for each step there is going to be a cost, and let's say that cost is represented by some kind of a array, right? Because you have to represent the cost for that array. So suppose the cost is whatever, this 2, 1, 1, 2, 2, something like this. And we have to pass this cost. And we have to say that when the person begins from the step 0, when the person whatever begins from the source, and this is, let's say, the step 1, 2, 3, 4, and when the person finishes this and reaches this destination here, then what is the minimum cost to cross this whole array? So we're going to write a function to do that. Right, so let's define this function. Once again, I'm going to define a function, and that function is called, let's say, min underscore cost. And it takes a cost array in itself. Now, first thing is I need to initialize something, right? So let me write the algorithm for this. Right. So step number one is basically create a cache the same size as cost. You don't need to in this case, but I'm just doing it because essentially you're just concerned with the last two elements, not the whole cache, but still that's okay. So create the cache of same size as cost, then basically initialize the first element of cache. Then third, from second to last element, compute the minimum cost for each step on the way. And fourth, finally, when you have reached the end of the array, return the minimum of last versus second last element. Is there any question on this algorithm? Once again, I'm doing the bottom-up approach right now. All right, and the top-down is going to, something I'm going to give you as an assignment so that you guys also run your brain and get some practice. So let's begin. The first thing that I'm going to do is I'm going to say memo equals to, I'm going to initialize an array, right? So first of all, let's just say L equals to len of costs. First, I'm going to compute quickly the length of this cost. And then I'm going to say memo is equals to initialize an array multiplied by, let's say, L plus 1, right? I do L plus 1. Why do I do L plus 1? Because I am going to use one. Actually, let's just do this. 0 multiplied by L. That's good enough. Right. Yeah. Let's see. Now, let's say print off this memo. So just to be clear that we are getting a 2D array, let's just print it. 1 second. What did we do? Oh, sorry. Incorrect variable naming. Let's run this code. And there you go. That's the array. To just for the sake of it, let's define a smaller size array first so that we don't have to worry about this. 1, 2, and let's say that's it. 1, 2. Let's just do a smaller size array for now. Now, let's run this again and make sure that we have the correct thing. Yes, correct. So now, what we need to do is, we need to, just give me a second, just give me 1 second. All right, just give me 1 second. I'm having some difficulty with my keypad. All right, yeah, I think this is fixed. Yes, it's fixed. All right. So let's get rid of this and let's initialize. We have created an array of the same size. Now let's initialize. So memo of 0 is equals to costs of 0, right? the smallest cost to get to the first step is that element itself, right? And the memo of 1 is equals to, let's go back here. What would be the cost to get to the element number 1? So just to put some perspective here, so this is, for our implementation, this is 0, this is 1, 2, 3, 4. These are the indexes like this. So I initialize the 0 with whatever the cost is. So I initialize this with 1. What would be the minimum cost to get to this second step, which is the index 1? Same, right? Exactly. It's going to be same. You just jump to that position. There's no point going previous positions. Now I'm going to iterate over the rest of the array. I'm going to say for x in range from 2 to L. Let's go from 2 to L. Each item, okay, I need to write memo of this item. This particular item is equals to. Can anybody tell me the expression I should write here? For this particular item, the cost, the minimum cost to get to this item, all right, is at least the costs of x. This has to be there because that is the cost of this particular step. And the minimum of either the previous step or the second to last step. That's how you construct each element of this array. Any questions on this particular statement? If it's not clear. Once you have constructed this whole array, okay, let's just, before returning the answer, let's just print. Okay, let's print memo. And let's make this 2. Let's run this. So that's the minimum cost to get to each step. That's the memo. So minimum cost to get to first step is this. Let's just also print cost so it will become clear. So it will print above and below. Just give me a second. Sorry about that. Let's write this. So these are the steps. Step 1 is 1, step 2 is 2, and the minimum cost to get to step 3 is 3, right? You can understand this. We are taking 2 from here, and then whatever is the robot is jumping from 1 to 2 to get to this position. And so the minimum cost to get to that step is 3 based on the recent previous history. Now, how should I return the answer? Right, we have this. Let's just print it once again. We have this. How should I return the answer now? Can anybody tell me what can be the answer here?
The last element.
Sorry, didn't hear. What was that? Somebody said the answer, but I could not hear.
The last element.
Will it be the last element? Can there be a case where the last element is returning wrong cost? Maybe let's say 10, 20, and 30. Let's take this case, all right, and run this case. Now, what is the minimum cost to cross this array? What would be the minimum cost to cross this array?
30.
It will be 30. So once again, let's just delete it. You have 3 steps, 10, 20, 30 is the cost. There's a person here, needs to get here. What is the minimum cost to cross this?
40.
40, because you can jump here and then you can jump here and then come here. That's 40, right? Why can't you just jump here and then jump here? That's 20, right? Isn't that the case?
Yeah.
Right. So once you have computed the minimum cost for the whole array, right? The minimum cost to get to here is this. The minimum cost to get to here is this. Sorry, this, and the minimum cost to get to here is, let's say, 40. Then whatever is the last two, that person can jump from the last two, right? So whatever is the minimum of these two is the answer, isn't it? So I can just return.
Yes, the answer is the minimum of last two.
Sorry, was that? Your voice is breaking up, so I could not hear properly again.
The answer is the minimum of last two elements.
Yes, exactly. So minimum of memo of the very last element. In Python, you write it as -1, comma, memo of the second last element, which is -2. So return that. And that is your answer. Let me make sure I print it. Let's run this. And then the minimum answer, the answer is 20. So let's get rid of this guy and let's bring in the bigger array and let's see. So this is how it constructs. That's the minimum cost to get to each of these steps. And once the array is finished, the minimum cost to finish the whole array is either minimum of 6 or 8. So you will choose 6 to get to the end. All right, I'm gonna give you a minute, all right? Or maybe 30 seconds, whatever you want. Look at the solution and see if you have any questions, if anything troubles you. All right, so who can tell me the time complexity for this code? What would be the time complexity of this code?
Linear time. N.
Yes, n, right? Because how many computations we are doing? We are doing n computations, and each computation is constant time computation. So there is n, O of n is the time complexity. All right. And what is the space complexity for this?
N as well.
N as well, that's correct. So for an array of size n, right? So 1, 2, whatever, n size, we are writing one for loop that begins at this position and goes all the way to here. And for each element, it's doing a computation, an addition and a minimum of the 2, which is a constant time of operation. So at each step, you're doing O1 of work. O1 of work. and O1 of work, and that is repeated n times, which is O of n times. Similarly, in order to solve this problem, you created an array of size n, right? So that tells us that there's a O of n space complexity to solve this problem. All right, now the similar problem, since you solved this, the similar problem goes for a 2D world. I'm not going to solve this. I'm just going to show you real quick. Once again, it's a standard problem. So instead of, we just solve this problem right now. We solved a problem where you had to find all the paths. But the problem changes and it becomes that to each cell, there is a cost. For example, 1, 5, 0, 2, whatever, and ... all these cells have some cost to it. Then what is the minimum cost in which you can reach from source to destination is the question. The similar question comes. It can be asked in the form of a map, right? In form of a graph where you are sitting at a source and you have some neighbors. And in order to visit each neighbor, there is a cost on the path, right? So you basically, whatever this 2 node, 3 node, there's a cost associated to get to 2 and 3. And then there would be some kind of a graph. There'd be some kind of a destination. And then what is the minimum cost to get to the destination? We will see this problem, this particular instance of problem when we talk about graphs later on in these talks. But essentially the problem is same. You can solve it in linear time. Now, or maybe, sorry, not linear time, but polynomial time, I mean to say. So this is a class of problem where we compute the minimum cost. And I will send you the link to these problems as well on Discord. There is a very good problem that got asked on lead code, which is kind of similar to, I don't know if you guys know about the knapsack problem, but I will send you the link. You'll find it interesting. It has player age and player ranking, and then you have to do, under some constraints, you have to select a team. I will share it on Discord so you guys can visit it. Now, I want to come to the third category of problem in DP. Now, clearly, I will not be able to finish it. And the next session is on trees, so I will find an extra slot to bring this in. But the third class of problems are something of this type. Suppose you have a string. All right, suppose you have a string which is whatever, x, y, z, ... b, a, c, c, a, b, and then ... whatever. And the question is, find the biggest palindrome in this string. Find the biggest palindrome in this string. So there might be several palindromes present, but you have to find the one which is the biggest length palindrome. Or the question can be, what is the size of the largest palindrome in the string? That's actually usually the question. What is the size of the largest palindrome in this string? Now, if you try to do this the naive way, all right, so then what you will end up doing is, suppose there is a string. Let's say there is a string, which is a palindrome. Then if you write a basic code to check palindrome, right? Basic code to check palindrome, then what you will essentially do is you'll write some kind of a loop that compares the first and last element, second last to second last element, iterators goes from left to right, right to left, and then essentially once they cross, you know that it's a palindrome because all the characters are same, except the middle character. So that check can be done in O(n) time. Now, the brute force approach would be to generate all possible substrings for this string. All the possible substrings for this string. All the possible substrings can be generated in O of n squared time. And within that, you can check whether a string is palindrome or not in O(n) time, leading to an O of n cube time to do this problem. That's the brute force approach of doing it. Plus the space separately when you construct the new strings. Now there is, I mean, of course, I'm covering it so you can solve it with DP, and the DP reduces the time complexity. I will cover the solution and then I will explain how that works. But so currently, I think we are only 2 minutes left in the session. So I'm going to stop here. Okay. And what I'm going to do is I'm going to find a new slot and schedule just a meeting for the remaining of the DP. I will not take it on the usual time because the next week's slot is reserved for the trees, the binary trees, and people are already, I think, signing up on that session. So I don't want to cause trouble for them, but let's see. Where is this? Events.